Welcome to today's Explainer. We're diving straight into what is honestly one of the most awe-inspiring and high-stakes operations in all of modern engineering. I mean, picture this. You're standing on a vessel out in the middle of a hostile, rolling ocean. And your job? Your job is to take a massive steel structure weighing up to 20,000 tons and accurately drop it onto the seabed hundreds of meters below. Welcome to Offshore Installation Day. It's this crazy process where literally years of meticulous design and mathematical simulation all come together in just a few hours of absolutely breathtaking, adrenaline-fueled action. So today, we're going to break down exactly how these colossal fixed steel jacket platforms, the absolute workhorses of the offshore industry, make that terrifying transition from a floating barge to a permanent rock-solid home in the ocean. All right, so here is our mission blueprint for today. We're going to follow this platform's journey chronologically. First, we'll look at the installation challenge, then we'll compare lift versus launch. After that, we'll get into the actual engineering ballet, followed by pinning to the seabed, and finally installing the topsides. Okay, let's kick things off with Section 1, the installation challenge.
So, the scene is set. The transport barge has finally arrived on location. The anchor-handling tugs have already deployed the barge's moorings. The whole installation team is on site and, well, now comes the absolute most dangerous and spectacular phase. Just like the quote says, getting a 20,000-ton steel structure off the barge and onto the seabed. Think about the sheer scale of that for a second. Moving this colossal steel jacket from lying completely flat on a transit barge to a vertical resting place deep in the ocean requires absolute pin-drop precision. There is zero room for error here. One wrong move, maybe a slightly miscalculated center of gravity, or even just an unexpected shift in the weather, you could literally lose an asset worth hundreds of millions of dollars. The extreme danger of this specific moment, it really can't be overstated.
Which brings us to Section 2, lift versus launch. Now, what's really interesting about this slide is seeing the contrast between the two main ways we actually get these giants into the water. Basically, it's completely dictated by size. For your small to medium jackets, a crane vessel, like a semi-sub or a crane barge, can just lift the jacket right off the transport barge and lower it vertically down to the seabed. It's clean, it's controlled, and it's incredibly precise. But what happens when a jacket gets so massive that it exceeds crane capacities? Well, we can't lift it. Instead, we actually have to slide it or launch it directly into the ocean. It is wild. And that dynamic sequence takes us right into Section 3, the engineering ballet. Okay, so to actually pull off this launch, the transport barge is intentionally tilted. How? They literally flood its own ballast tanks on one side. As the barge tips, this massive steel jacket, which is still lying horizontally, just begins to slide right off the end of the barge, gliding down these specially greased launch runners. And let me tell you, the sheer kinetic energy when thousands of tons of steel hit the open ocean, it looks completely out of control. It looks chaotic. But the truth is, every single millimeter of this movement has been intensely calculated because as soon as it hits the water, the jacket's own geometry completely takes over. It's designed so that one end sinks faster, which naturally forces the whole structure to rotate right into a vertical orientation. This uprighting sequence is this perfectly choreographed ballet, entirely controlled by its own buoyancy legs and these pre-installed flooding valves. During the few seconds and minutes of this sequence, literally years of calculations, simulations, and planning are put to the ultimate test. And if all goes perfectly, the structure magically uprights itself and just floats there vertically in the water column, completely stable. So now it's vertical and floating. What's next? Well, the floating jacket has to be carefully maneuvered to its precise target position using tugs and guide wires. Then they slowly ballast it down to the seabed by flooding its internal compartments. As this giant structure nears the bottom, remotely operated vehicles, or ROVs, and sometimes even actual human divers, are deployed to watch the final touchdown. Their job is crucial. They have to confirm that the jacket is resting perfectly on its steel mud mats. And if you're wondering what those are, they're basically these large steel grids welded to the base of the legs that safely distribute all that massive weight across the soft seabed surface. Moving right along to Section 4, pinning to the seabed. All right, think of the jacket as a giant tent frame. And just like a tent, it is completely useless against huge, continuous ocean waves and currents if it doesn't have tent pegs, right? Well, our tent pegs are these massive steel foundation tubes, and they are lowered directly down through the jacket's legs. To actually drive these pegs deep into the seabed, they bring in a massive hydraulic pile hammer, usually an IHC or a Menk hammer, that's suspended from a crane vessel. It literally hammers these colossal steel tubes straight down into the earth with the energy of a small bomb. And we really need to talk about the scale of these pegs for a second. These steel tubes are absolute monsters. We're talking 1 to 2 meters in diameter with solid steel wall thicknesses of up to 100 millimeters. The hammer just relentlessly strikes the top of the pile at an exhausting 30 to 60 blows per minute. And while this is happening, you've got geotechnical engineers glued to the data, carefully monitoring the driving record, which is the exact penetration achieved per blow. They check this against their predictions to guarantee the pile is hitting the correct soil layers and achieving the required bearing capacity so the platform will be perfectly safe.
Finally, we reach Section 5, installing the topsides. Okay, so the piles are driven and the jacket is securely pinned to the ocean floor. Now we can finally move to the topsides, the actual working part of the platform. These are entirely fabricated onshore, sometimes literally on the other side of the planet, and then shipped over. But before we get to the lifting, I want you to consider this mind-blowing number. Offshore installation time is ridiculously expensive. Hiring a massive semi-sub crane vessel, that day rate can run you anywhere from $300,000 to $600,000 every single day. That kind of intense financial pressure completely dictates every single engineering decision made out on the water.
And exactly because of those eye-watering costs, modern projects are increasingly leaning toward what's called a single lift for the topsides, rather than the old multi-module assemblies. So instead of assembling it in separate pieces out at sea, the entire topside is put together as one massive, fully integrated unit back on land. Then, one of those huge semi-sub crane vessels, we're talking ones with a 5,000 to 14,000 ton lift capacity, positions itself alongside our jacket and lifts the entire topside into place in one single piece. It slashes that incredibly expensive offshore installation time drastically.
So as you can see here, let's just visually retrace the incredible journey we just took today. Starting way down at the seabed, you have the massive load safely distributed by the mudmats. Driven right through those legs are our giant foundation piles, firmly pinning the entire structure against the ocean's strongest forces. Then, rising majestically through the water column, you have the tubular steel jacket framework itself. And finally, sitting high above the splash zone, completely clear of the water, are the fully integrated topsides. And just like that, the 20,000-ton engineering ballet is officially complete.
But here's the thing. A giant steel island sitting out in the ocean is essentially useless if it doesn't actually do anything, right? The structure is set, but how do we systematically test it? How do we safely introduce highly combustible hydrocarbons for the very first time? Once those topsides are in place, the whole process of hookup and commissioning kicks off. It's a massive, fascinating puzzle of connecting thousands of pipes and cables, and we will absolutely decode all of that in our next explainer. Thanks so much for joining us on this incredible journey from barge to seabed. See you next time.